Well, hello everybody again to the second talk of Professor Claessen from the University of Würzburg. Yesterday he told us about the beauty and the power of photoelectron spectroscopy, and today we'll certainly hear how useful this technique is in studying real materials as, for example, oxides. Ralf, please.
Yes, thank you very much. As you said, yesterday I have been trying to give a pedagogical introduction to the method itself. Today I want to show you a number of applications as examples, starting with the canonical LaO SDO system, and then I will focus on more correlated oxides such as lanthanum titanate, strontium vinodate, and if time allows also strontium iridate. Before I go into the details, let me just acknowledge the team that has contributed to all these experiments. And this is my group in Würzburg here with a lot of people, postdocs and PhD students contributing. I don't want to go into details here. A lot of the work that we have been doing has been done not just in the laboratory, but we have done photoemission experiments at various synchrotron radiation sources. We have our own HAXPES setup at Petra 3 in Hamburg. At DESY, we have been closely collaborating with, or are still closely collaborating with the Diamond Light Source in the UK, and we did experiments at the Swiss Light Source at Spring 8. These days, we grow the films and heterostructures ourselves, but when we started this field, to work in this field, we had very fruitful collaborations with a number of people, in particular with our chairman, with Jochen Mannhardt, who I shared some time with at the University of Augsburg before I came to Würzburg, and he kind of introduced us to the wonderful world of oxide thin films. But we have also been enjoying collaborations with the group of Gus Reinders at the University of Twente and with Nini Pritz at Copenhagen. Okay, so this was the wrap up of yesterday. Photoelectron spectroscopy gives you information about a number of things, starting with the chemical composition of the material and the depth profile that you can probe through in heterostructure and look at the interface properties. But in particular, and that's the main target of our investigations, you want to study the microscopic electronic structure, density of states, momentum resolved band structures, Fermi surfaces, and if you have strong correlation effects being at work, also the single particle spectral function. And there is this particular aspect for oxides, and in particular heterointerfaces of oxides, that you need a high probing depth, and for that we have to go to high photon energies, and that involves in particular the need for synchrotron radiation, which is intense enough and gives us the high energies that we need. And as we will see today, will also allow us to use a particular technique called resonant photoemission. Okay, and as I just mentioned, we will start with LaO SDO, the Drosophila system in this business. And I probably don't have to go into much detail here, or many of you will know about this. You have two large gap semiconducting materials, insulating materials, LaO and SDO. You combine them, and you find that at the interface, you find a high mobility electron gas. If the thickness of the LaO overlayer on the SDO substrate is high enough. There is a critical thickness of 4 unit cells from which on you get this high mobility, and you see the delocalized charge carriers in a Hall experiment. This 2-deck has a number of fascinating properties. It shows superconductivity at very low temperatures. You can control it with field effect. Some people have claimed to have observed ferromagnetism here in parallel to superconductivity, and a number of further things that really have made this a particular interesting, fascinating topic to study. The main picture that people always draw when you try to understand why does a two-dimensional electron system, a high mobility electron gas, develop at the interface of two insulators, is this picture here that takes into account the polar discontinuity that you have at the interface. Strontium titanate is an unpolar material, while LaO is a polar one because you have trivalent lanthanum and trivalent aluminum in it. And if you look at the charge distribution in these layers, if you decompose the perovskite structure in these layers, you find you have an alternating sequence of plus and minus 1 electronic charge per lateral unit cell. So if you then look at the implications for the electrostatics of the system, you find that if you integrate out the charge carrier density, you get this electric field distribution, and from that you can get then the electrostatic potential, and you find that this is increasing with the thickness. And if you go to macroscopic thicknesses of this film, you get an infinite amount of energy stored into the system, and that is of course not favorable for the system. That's called the polar catastrophe. This is the same phenomenon that drives the reconstructions at surfaces of polar materials. There's one way to circumvent this this polar catastrophe, and that is by transferring charge from the surface to the interface. Is not literally transferred from the surface, but there will be a rearrangement of the total charge in the LAO layer, which at the end renders some charge left positive. Some half an electron per unit cell here at the surface, and another half electron at the interface, sitting on the SDO side of the interface, and then you find that the electric field, and in particular a potential distribution, is such that it does no longer diverge. This is a simple classical picture, but you can of course also study the system by band structure calculation, and many groups have done this. And this is in principle the picture that you get from this. At the interface, you have a band banding situation, as you have it often in semiconductor heterostructures. So the SDO conduction band gets pushed down somewhat here as you approach the interface from the SDO side. And on the LAO side, because it's a polar material, you get this built-in potential that leads to an increase of both the valence band and the conduction band edges. And when the thickness exceeds a certain critical thickness, you can see that the valence band maximum crosses the Fermi level. These states here get depopulated, and these electrons will then look for the lowest possible energy states that they can occupy, and this happens to be this potential trough at the interface. And that's then what you expect to see. You depopulate the surface, and you end up with these electrons sitting in the conduction band of the SDO at the interface, forming this two-dimensional electron system. In order to make this happen, if you just look at the electrostatics, you expect to see half an electron per lateral unit cell, which translates into 3.5 times 10 to the 14 per square centimeters. And of course, you can then try to look at the actual carrier density, sheet carrier density that you have in a real device. And if you do that, you find that the Hall effect measurements give you a carrier density which is more than an order of magnitude smaller, which is a surprise, because that's not what you get from the band calculation. So something is incomplete in this picture here, and we will have to study this a little further. For that, of course, I will use photoemission spectroscopy, and the first thing that I will be looking at are the core levels, because that's the most easiest thing to do. And because we want to probe the interface here, which is some nanometers below the surface, I need high probing depth, and that's why we go to hard X-ray photoelectron spectroscopy. Right, here's the picture. We have a certain penetration depth. Here's my buried interface that I want to study, and I can only reach it if I have high enough photon energy. We do this here with 3 kiloelectron volts. And what I show you here is the spectrum of the titanium 2p core level. It's actually a doublet because of the strong spin-orbit coupling in the 2p shell. And in principle, if you would do the experiment on bare strontium titanate, you would just see 2 peaks, namely this one here, the 2p 3/2 and the 2p 1/2. But if you look a little bit more closely, you find that to the low binding energy side here of both peaks, you have a little additional spectral weight, and this is a blow up here this energy region, there's a little bit of intensity here. It doesn't look very spectacular, but it's completely reproducible and is only seen if you are above the critical threshold thickness in the LAO STO system. If you are below, it's gone. We can get a little bit more information by doing some depth profiling. As I told you yesterday, you can modulate or tune the probing depth by going to larger and larger escape angles, because then you simply you bend the path of the photoelectrons from the site of excitation towards the analyzer. And if you have a higher angle, if you have a finite angle with respect to the surface normal, this leads to a smaller probing depth. So as you go to higher angles, you shorten the exponential probing depth and become more sensitive to the interface layer. As you do this, you find that the intensity of this shoulder here is going up, and it's about 1 to 2 electrons at lower binding energy, and that's a typical sign that this is a different valency. Without any extra carriers, titanium would be in a 4+ valence state in STO. But if you add extra d electrons into the d shell, which is otherwise empty, you get a certain proportion of titanium 3+ ions in your system, and that's what we are seeing here. And from the angle dependence, we can directly conclude that they are localized at or near the interface here. You can actually try to do some quantitative analysis of this angle dependence, and we have done this quite excessively. And from that, you can then draw the conclusion that the thickness of the carriers is of the order of a few nanometers near the interface. And you can also extract the sheet carrier density in terms of electrons per square centimeter, and you find a number which is a little bit higher than you expect from the Hall effect, but still clearly lower than the 3.5 to times 10 to the 14 per square centimeter that you expect from a simple electronic reconstruction picture. Okay, so that's the core level, which is a probe of the amount of electrons sitting in the 3D valence shell. But why not looking at the 3D valence shell itself directly? And that's what we will do in the next chapter. And for that, we try to study the valence band. And this is what you get when you take your hard X-rays and you look at the energy region where you expect the valence band to sit, and then you get this signal here. You have this huge peak here between approximately 3 electron volts to almost 10 electron volts, and then you have a large gap here, and nothing within the noise and the statistics of your data happens as you go towards the Fermi level. Now, we would have expected to see a little bit of signal here because we know that there is some interface electrons sitting here which are conducting, so they're bound to be at the Fermi level, but we don't see them. Now, first of all, what do we see here at all? And of course, the LAO also has some electronic structure. It's a large gap insulator, but nonetheless, it has a valence band. It has a valence band that is governed by the oxygen 2p states. And what we see here, the most of the signal that we see here is coming from the LAO valence band. And then there is this little bit of contribution, and you can actually decompose this. I don't have the time to discuss this in detail, but a little bit of this this intensity here is due to the oxygen 2p states in the STO. And then you would also expect to see a little bit of the 3D electrons here. Now, there are two obstacles to this, to seeing the 3D electrons. One is that they are deep in here in the lower layer. That's why we have been using this high photon energy in the first place. And the other one is we don't have that many electrons. There is only 1/10 of an electron per titanium atom at the surface if you believe in the Hall effect measurements. And you can calculate what intensity would we expect, and you find it's 5 orders of magnitude less than you see here for the oxygen 2p states. So that it's very difficult to see it by just doing the HAXPES here. There is another interesting point before I try to show you how we can nonetheless see the titanium 3D electrons, and that's the very fact that we see this 3.1 electron volt gap here. Because if you remember the picture that we had before from the band structure theory, where you recover this electronic reconstruction picture that there is some bending band slope here on the LAO side, and that the valence band of the LAO eventually will cross the Fermi level, you would expect to see the carriers that are produced by that, or the Fermi energy intensity that is created here as the band crosses the Fermi level. And because we have an exponential probing depth, the surface of the LAO should contribute strongest to our signal. But as you can see, there is nothing here in this region. What we see here tells us that the onset of the valence band of the LAO is really shifted from the Fermi level by this 3 electron volts. So rather than this situation, what we are seeing here in our spectrum is this situation where the valence band maximum here is 3 electron volts away from the Fermi level. We have an almost flat band situation in the LAO. There is no evidence for a built-in electrical field, at least not from the spectroscopy. So that's why we think that this simple naive band structure picture cannot be correct. But let's go back to the question if we cannot see the titanium 3D electrons. One of the problems that we have is as we go to higher photon energies in order to get the high probing depth that we need, this was the universal curve that I discussed yesterday, and we are now somewhere here in this region where we probe of the order of a few nanometers, 20, 30 angstroms deep, we have a dramatic decrease of the cross-sections, photo excitation cross-sections of the various orbitals that we want to look at. This is titanium 2p, that's the core level that we have been looking at. That's oxygen 2p and titanium 3d. And you can see this is a logarithmic scale here for the photoionization cross-section, that this is dramatically decreasing as we go to these high energies, like proportional to the energy to the -3rd. So this kills our intensity here, and so we have to think about some trick how we can get this higher. Now the cross section that this has been calculated here is basically this dipole transition matrix element that we discussed yesterday when I did a little bit of photoemission theory, but we can utilize a second photoexcitation mechanism that is not captured by the simple dipole transition matrix element, and that's called resonant photoemission. And that's something that I would like to discuss in the following. Before I discuss the details, let me just show the effect of it. We go away from our hard X-rays at 3.5 kilovolts to somewhat lower energy, around 450 to 460 electron volts. These are 2 photon energies, just one at around a little bit lower than 450. That's the red one. That looks not so different from what we see at these hard X-ray energies. And there's basically no intensity here at the Fermi level. But if we increase the photon energy by just a few electron volts, you see suddenly, it's this blue spectrum, there is some intensity popping up at the Fermi level. Sharp peak, which is cut off by a Fermi Dirac distribution function, a clear indication that we have some metallic density of states here. And what's going on? Why do we suddenly see some intensity here? This is shown here. We have 2 processes which interfere with each other quantum mechanically. The usual photoemission process is the following one. Here we have our electronic structure in a very schematic view. This is our core level, a 2p titanium 2p core level. This is the titanium 3D shell, and with the T2G and the EG states. And if there are some 3D electrons doped into this interface, then there should be electrons sitting that we can excite here from the T2T levels into the vacuum and then detect at our detector. If the photon energy, however, is high enough that we can also excite this 2p core electron into an empty 3D state, for example, into the EG manifold or into the empty T2G states, then we reach such an intermediate state here, an absorption, a final state. But that is not, this is clearly an excited state for the system, and this will decay via an Auger process by one of these electrons here in the 3D shell falling back into our core hole, filling it up. But then, of course, the energy has to go someplace and will be transferred via Coulomb interaction. That's a typical interaction mechanism in an Auger decay, transfers it to the other 3D electron, which then gets excited into the vacuum, and the state that you reach here is exactly the same as the one that you create by the direct photoemission process. It's indistinguishable. So you have, if the photon energy is high enough to create this intermediate absorption state, you have two quantum mechanical processes which interfere with each other, like in a double slit experiment where the two where the electron going to two slits interferes with itself. And you can describe this by this expression here that you can derive from Fermi's golden rule. Again, by time-dependent perturbation theory. And you have now, besides this normal dipole transition, the second term that describes the absorption into this intermediate state and the subsequent decay through an Auger process. And you have an energy denominator here that, if you are very close to the absorption threshold here, becomes very, very small. And then this term here becomes dominating. In principle, these two terms can interfere, but it turns out that in transition metals, especially 3D transition metals, when you go to the L edge where you excite a 2p electron into the 3D shell, this is by far the dominating term here. The actual interference or quantum beat between these two processes is very small, because this is just killing the other part. You can by that reach an intensity enhancement by almost 2 orders of magnitude. So it's a strong enhancement, and it's extremely sensitive to the fact that these are 3D electrons, because it's this 3D shell that couples directly with this 2p 3D excitation. So you have an orbital specific, very strong enhancement of intensity, and that's what's happening here in this experiment. And I show you here in the next slide a systematic series. I show you the entire valence band. As we increase the photon energy, we go from 455.5 to 460. We go through the titanium L edge in such an LaO structure. And you see that we have intensity popping up quite dramatically at very specific photon energies. And I will blow up this region here. This is the oxygen 2p part, but we are interested now in the titanium 3D signal. And this is the blow up region here. And apparently there are two signals that we detect which get resonantly enhanced. There is one directly at the Fermi energy, which is cut off by the Fermi function, which is due to the delocalized carriers. And there is a second state here at approximately 1.4 electron volts, which we in the following we just call in-gap state. And I will say a little bit about its nature in the next few slides. This is just another representation of these data as a false color plot. Blue means high intensity, red means zero intensity. And as we increase the photon energy, you can see that we have this peak, this in-gap intensity peaking at 459 electron volt photon energy. And we have this very narrow peak at the Fermi level, which peaks at a somewhat higher photon energy, 460 electron volts. And you can compare this. This is the intensity of these two states. The black one is the in-gap state. The blue one is the quasi-particles, the metallic quasi-particles here at the Fermi level. And this is in comparison the bare X-ray absorption spectrum. And you can see that the in-gap state very closely tracks the intensity of the absorption that you measure in a trivalent titanate. This is not LaO, this is lanthanum titanate, where titanium is in a 3+ state. While the quasi-particle peak is a little bit shifted by 1 electron volt and resembling a little bit more what you expect in the absorption spectrum of a 4+ titanium valence. The fact that we have here two different resonance energies for the in-gap and the quasi-particle state is something that I will be using in some of the next experiments. But let me first identify these two peaks. The one at 1.4 electron volts, we interpret as due to localized titanium 3D electrons, which are trapped by oxygen vacancies. We will discuss the role of oxygen vacancies in LAO SDO in the next section, but we know that there are some vacancies, and if you have one sitting close to the interface, it will trap some of the 3D electrons in neighboring titanium atoms, and that's why they have this relatively large binding energy. But there will also be itinerant carriers sitting in the 3D band at the Fermi level and can contribute then to the conductivity and to the high mobility 2-deck. Okay, so we have in-gap states, we have quasi-particle states. By the way, both of these states have been known before from bare SDO, because if you take bare SDO and you render it a little bit oxygen deficient, you also see these two types of peaks in photoemission spectroscopy. Now let's do a little bit more on these 3D states, because if the quasi-particle peak is really due to the metallic band, then we should be seeing some momentum dependence, and that I will do next. We use the high photon energy that we use here at the resonance condition. At the same time, also detect photoelectrons for their angle of emission or their momentum, as we had discussed yesterday. And if you do this, and for example, if you track the evolution of the momentum along this line in the Brion zone from gamma to X in the rectangular surface Brion zone and then into the next zone, you see these kinds of spectra here. You see as you go along the path here some intensity around zero momentum, and then it's decaying again. You have virtually no emission, and then you go into the second zone and reach the second gamma point, and you see again intensity popping up. And you can turn this into a band structure using false color representation and compare this to band calculations. And you see here we have some 3D electron band here, which then apparently crosses the Fermi level and again comes back in the second Brion zone. Now, as you can also clearly see, this is the band calculation from Thilo Kopp and Natalia Pavlenko. When they have a much richer fine structure in their band structure, which is due to the quantum well states that form in the potential trough in the strontium titanate interface side. In our experiment, we do not have the resolution to resolve all these fine details. That's due to the fact that's the price we pay by going to these higher photon energies, where so far we do not have yet the same experimental resolution as you have it in low energy photoemission. But nonetheless, you can clearly track the existence of these electron pockets. You can go into another path here. This is going through the diagonal, or more or less the diagonal of your Brion zone, and you see again we have some intensity electron pocket at gamma. And then you can also do Fermi surface mapping by just fixing your energy at the Fermi level. This is the band here, and fixing the energy at the Fermi level, and just looking for where do we see some intensity, and then you again render all these electron pockets at the gamma points of the various Brion zones. You can also go to higher order Brion zones. Again, as I said before, the resolution is limited in these high energy experiments. For comparison, I show on the right hand side the Fermi surface that we have measured on oxygen depleted SDO with low energy HAXPES, where you can see all the fine details of the various D bands, the T2G bands in the surface there. You can barely see this cross-typed intensity distribution here. We cannot clearly resolve it, but clearly what we can say is we have electron pockets around the gamma points. You can then compare this to band calculations. This is done here. And so there is, there is agreement within the resolution, of course. We have these electron pockets also predicted in the band calculation due to these electrons sitting here in this potential trough. But as I said before, in the band picture, you would expect the LAO valence band to cross the Fermi level and to give rise to hole-type Fermi surfaces at surface. And according to the band calculation, they should be centered around the endpoints. So we should be seeing some intensity here that crosses the Fermi level, some Fermi surface, and clearly we don't see it. which agrees with our former observation of the density of states that clearly this LAO band, valence band, does not cross the Fermi level. So we have rather a cross-section, a flat band situation here, where the LAO valence band always stays below the Fermi energy. Then, of course, one can ask the questions: if that band never crosses the Fermi level, where do these electrons come from that populate the strontium titanate potential trough? And there are some arguments, and I don't have time to go into details, and also some calculations for off-stoichiometric LAO-STO that oxygen vacancies at the surface of the LAO, and it turns out that the energy for formation of such vacancies is the lowest at the LAO surface, could be responsible for this. They would pull off states from the valence band maximum, shift them all the way across the gap. They would end up above the Fermi level, so they would be empty states. And the depopulation of these states then leads to the filling of the 3D shell here. Okay, I think this is what I wanted to say about the band situation, but I was mentioning this in-gap state, so which is due to oxygen vacancies on the STO side. In the following, I will discuss a little bit the role of oxygen vacancies in the STO, not in the LAO, but in the STO, where we are most sensitive when we do resident photoemission to the titanium 3D states. And we can ask ourselves, what would an oxygen vacancy lead to? Now you have an ionic compound where the oxygen lives as an oxygen 2- ion in the lattice, and if you take an oxygen out, it will eventually end up as half of an oxygen neutral oxygen molecule. These 2 electrons of the former ion will be left, 2 extra electrons, which then eventually leads to some N-doping of the residual system. And all the sites where an oxygen has been lost is now a defect, a point defect, which against the the charged background in our ionic compound acts like a positively charged point defect. And it has been known from studies of bulk STO that oxygen defects cause strong effects. For example, a stoichiometric STO crystal would be transparent. It has a full gap, but as soon as you take oxygens out, you dope the system with extra carriers. It becomes metallic, and it's no longer transparent, but turns black. And that there is some effect of the oxygen stoichiometry has also been known from transport experiments on LAO-STO. This is an early study by Alexander Brinkmann in Twente, where they have grown LAO-STO under various oxygen pressures during PLD growth. This is going from low oxygen pressure to high oxygen pressure, and low oxygen pressure means there is not enough oxygen available, so the LAO-STO will grow oxygen poor, and then you get this highly conducting. This is the resistance shown here. So lower resistance means a strong conductivity, highly conducting situation due to the oxygen vacancies in the system that dope the system. And as you go to oxygen-rich conditions, which lead to a more stoichiometric behavior of the STO, you see this strong increase in resistivity and resistance by orders of magnitude, and also here this little increase here that has been interpreted in terms of condo type behavior. Okay, but can we see this in experiment, in photoemission? And of course we can see it. This is again the 2p core level, where we have seen this trivalent satellite in LAO-STO. And if we look at LAO-STO samples that have been grown with different amounts of oxygen pressure during growth, high oxygen pressure means 10 to the minus 1 millibar, low pressure means 10 to the minus 5 millibar. You can see here that the intensity of the trivalent satellite increases as you go from high pressure to low pressure. Again, low pressure means we don't have enough oxygen, so we create oxygen vacancies, apparently here on the STO side, because we are looking at a titanium signal. And obviously, there is some electron doping into the into the 3D shell because we have an increase of titanium-3+ signal, which means the 3D shell is in a D1 configuration and not D0 as you would expect from bulk SDO. By the way, the black curve here is bulk SDO, where you have no 3+ signal whatsoever. Now this can actually be tuned in our experiment, and for that we have used this spectacular beamline at the diamond light source. It's a so-called 2-color beamline. It shows you just as a glimpse what a synchrotron Photoemission beamline looks like. You have here in the background your accelerator. The electrons with nearly the velocity of light go through these 2 undulators. There are 2 of them. You can see they are slightly tilted. The first one produces this red beam here. That's branch 1. That's our hard X-ray branch. Goes through some crystal monochromator, some focusing, and then reaches the sample. And we will use this hard X-ray beam, which is delivers photons in the kilo electron volt regime, to change our oxygen stoichiometry. And then there is a second beam here. That's the blue one that produces soft X-rays. That's the region where we can do this resonant photoemission experiment. Again, you have a monochromator, you have some focusing mirrors, and then you focus on the sample. And the trick here is that you focus both beams on exactly the same location on the sample. Now you have to know that the photon spots are of the order of a few microns. So it's typically 10 micron diameter. And both photon spots are aligned in such a way that they're really overlapping. They light up the same region of the sample within micron precision, but the distance from the light generating undulators to the sample is 70 meters. So that's really a macroscopic distance, but then at the end, my colleagues here at the Diamond Light Source achieved to focus this within microns on the same spot. That's spectacular. Okay, what happens if you irradiate light on your sample? I haven't mentioned this before. When you do photoemission, especially with hard X-rays, you create also beam damages. And when you do your experiment, when you do spectroscopy, you have to be sure, or you have to monitor the effect of such beam damage. You want to, typically if you do spectroscopy, you want to avoid this beam damage. In our case now, we want to utilize it. And I show you what happens here when we start out with some sample, say in this black situation here, which has been irradiated for 1 minute in order to accumulate these data. You see a little bit of 3+ signal, and then you start taking longer and longer spectra, 15 minutes, 30 minutes, 45, 60 minutes, and you see that there is an increase and eventual saturation of the 3+ signal. So that means that we create oxygen vacancies here, and that is known. That's the Nortek-Feiberman mechanism. It was mentioned a few days ago by Ulrike Diebold. When you shine high energy light on an oxide, you very often create oxygen vacancies, and that's what's happening here. However, we can fill these oxygen vacancies again with oxygen. So we have severe oxygen depletion by the light, but we can fill this again by putting a metal capillary very close to the surface and put some oxygen gas here on our sample. Then this leads to reoxidation of the surface, the quenching of these vacancies. And if you then take a spectrum, you can see that's the blue one here. That's after exposing the oxygen. It's actually while we are exposing the oxygen. We can do this simultaneously, taking the data and exposing it to oxygen. You see that we can strongly reduce the titanium-3+ signal, which is a clear signal that for reducing the density of oxygen vacancies. So we have a full in situ control while we are doing our experiment of the oxygen stoichiometry at the interface. And that's what we're doing now here to study the effect on the quasi-particle and the in-gap state. And I will start with the top panel here, which is taken at this particular energy. This is the energy where the quasi-particle, the metallic carriers here at the Fermi level, are most strongly resonating. We start with this black spectrum here. We have a little bit of intensity here, so there is already some carrier density to begin with. And then as we increase our hard X-ray irradiation to generate these oxygen vacancies, we can then probe the surface with a soft X-ray beam. We're doing this resonant photoemission experiment, and you see that the signal of the quasi-particles increases very strongly. We do not see much here for the in-gap state, and that's simply because we are working at the quasi-particle resonance, which is most sensitive to this energy region. We can, of course, change the photon energy to be more sensitive to the in-gap region. And here you can see, as we increase, as we go to increasing amounts of hard X-ray dosage, we create an increase in intensity of the in-gap weight, and that tells us that we create oxygen vacancies. Now, if we expose the system again with the oxygen using this oxygen oxidation capillary, you can see that we can quench the spectra back to the original situation. Here with oxygen is the blue spectrum. We end up with the same situation that we started out, which is the black spectrum. And the same is true here for the situation where we probe the in-gap state. We can completely quench the in-gap state. We cannot completely quench the quasi-particle state. It goes back to its original height. For the in-gap state, we find we can really quench it down to almost zero intensity. This is very different to the bare STO surface. If you do the experiment on just a bare STO substrate with no LAO on the surface, you can start out with a spectrum where you have no intensity in the entire gap. So there is no quasi-particle, there is no in-gap state, because it's a band insulator with no carriers in it. And then by the hard X-ray beam, you create these oxygen vacancies, and you find that you have both the quasi-particle intensity as well as the in-gap state going up here in intensity, just as we see it in the LAO-STO. But when you then offer the extra oxygen, you can quench both the quasi-particle peak, both the in-gap peak as well as the quasi-particle peak down to zero completely. So this is, you can quench it back to a real insulator. While in the LAO-STO, you are always left, independent of how much and how strongly you expose the system to oxygen, you're always left with a finite amount of quasi-particle intensity, which tells us there must be some, even if you fully oxidize your system, if we have no oxygen vacancies in the system, there is some intrinsic component of the two-dimensional electron system that is not related to oxygen vacancies, which may come from the electronic reconstruction mechanism, or, as we speculate, comes from other defects in the LAO. I may come back to this. This is the same data represented in the same way. This is the STO, the bare STO sample with both the quasi-particle and the in-gap state. As you expose it, you find an increasing amount of intensity, and then you start oxidizing, and you can quench both signals. While in the LAO-STO state, you have here in green the in-gap weight and the quasi-particle weight, and the quasi-particle weight is always offset a little bit from the in-gap weight. And then as you start oxidizing the surface, you can completely quench the in-gap state. So you have no oxygen vacancies left that can cause an in-gap state, but there is still some residual intensity from the metallic quasi-particles. Okay. The reason, or the explanation for this, we cannot directly derive now from these measurements. There has been some speculation, there have been some band calculation by Alex Zunger's group, where they speculate that there are anti-site cation defects in the LAO that can provide the extra charge that you need to populate the 3D states on the in the STO at the interface. And the critical thickness of the LAO-STO is then related to the fact that the energy of formation for these anti-site defects is a function of this inner potential, or the polar discontinuity, I should rather say. So they can derive a very nice, relatively consistent picture out of this. So polar discontinuity plays a role here, but it's not the simple electronic reconstruction picture as was often sketched out. Okay, and now I want to switch gears here to correlated electrons, transition metal oxides, where the 3D shell is partially occupied and where the strong Coulomb interaction between the 3D electrons plays an important role. And for that, we have to discuss a little bit the theoretical frame or the conceptual frame to understand the data, and that's of course the Hubbard model, which I will quickly try to summarize here. I think most of you will be familiar with that. We start out with some lattice with atomic sites on it, which carry 3D electrons, and then you can occupy the sites here with electrons with spin up or spin down. They can hop from side to side because of this term here. This gives rise to the formation of kinetic energy. The system can gain kinetic energy from that, and that drives the itineracy of the electrons. And if we had only this term, we would have a simple tight binding description of our system. But then we have to take into account that if you have two 3D electrons sitting on the same side, there will be a strong Coulomb repulsion of these two electrons, and that costs energy. And this is described by this term here. And we condense all the Coulomb terms in this single number U. That's the local Coulomb energy that two electrons have to pay when they are on the same side. So such a situation here is energetically very costly. And now everything depends a little bit on how many electrons you have in your system. Let's take the situation where you have a band filling or a side filling of n equals 1. You have 1 electron per side. And if the U term would be 0, if we are in a situation of a plain tight binding description, we would have in this case a metal because we have a half-filled band. In principle, each band can host 2 electrons per side. If we have only 1, it's half-filled. And so we have a Fermi energy here. All states up to the Fermi energy are occupied, and the upper half of our band will be empty. We have clearly a metal. If we had no hopping at all, if we had just the U, so everything, there would be individual atoms, if you will, the system would be in a state where the lowest energy can be reached by placing exactly 1 electron at each side. Not just on average, but exactly on each side, there will be 1 electron. And then you would get this situation here. You would have this electron sitting at a certain binding energy. And if you want to place a second electron on the same side, you would have to pay this energy U, which is far away, and you would by that create a large gap here. And that's the background, or that's the explanation for the existence of a Mott insulator. Now, these are 2 limiting casing. None of them is ever reached in reality. So what happens if you have a finite T and a finite U as you go from the metal to this Mott, to the strict Mott insulator? And let's start with the metal situation. As you increase the U here, 2 things will happen. One is that you find some extra intensity here in the outer wings, which are the incipient Mott lower and upper Hubbard bands that will be forming here. And at the same time, our metallic density of states will shrink in width. This is nothing but the band renormalization that electrons experience in the presence of strong electron correlations. And as you go to stronger and stronger correlations, this band becomes increasingly narrower. The band mass will increase. That's the Brinkmann-Rice behavior, until eventually it will become infinitely small, so that there is 0 spectral weight contained in this quasi-particle peak, and you are left with just the lower and the upper Hubbard band with 0 spectral weight in the middle here. So if you go from there to there, it's not that you have just a splitting of spectral weight here into 2 individual peaks. You have actually a 3-peak structure with these narrow quasi-particles, which then will decrease, will lose their spectral weight as you increase the U over T ratio. Let's call it the bandwidth controlled Mott transition. The stronger this local Coulomb energy is with respect to your hopping term or your bandwidth, the more you will reach this Mott insulating situation. There is another way you can reach a metallic situation from a Mott insulator, and this is when you start to do depopulating or populating your system from the half-filled situation. Here I have depicted the case where we take electrons out of the system, so some of these sites will now be empty, and you can imagine that for some of these electrons it will become possible now to hop to neighboring sites because there is no other electron there, so I don't have to pay the Hubbard energy U. And in terms of spectral weight or the single particle spectrum, what will happen is that you start out with a Mott insulator. This is the situation half-filled, X equals 0, and then you start doping X holes into the system, and there will be a very narrow quasi-particle state evolving close to the lower Hubbard band, and it will fix the position of the chemical potential. And as you increase the doping, this band will broaden until at very strong doping levels, this quasi-particle peak will have eaten up all the spectral weight, which becomes subsequently transferred into this metallic peak here to render a simple or one electron-like density of states and band dispersions that you would be able to detect when you look at the momentum resolved spectral weight. That's called the band filling controlled Mott transition. So we have two ways to go away from a Mott insulator into a metallic regime, and that's depicted here in a very schematic phase diagram that comes from this famous review article by Imada and co-workers. This is the correlation strength, the U over T parameter. This is the band filling. Here we are at exactly a half-filled band, one electron in the D shell. If we are here at low correlation strength, we are in a metallic situation, but as U increases a certain characteristic threshold value, we run into a Mott insulating phase. And if you go away from half-filling, from D1, by either N doping or to P doping, and we will be looking at the P doping situation in the following examples. You can cross this line here also from going to a Mott insulator to a metal. It causes here you see here this bent phase boundary between the insulator and the metal. As you go to a doped situation, it will cost you more and more correlation energy to reach the Mott insulating state. So that's the framework in which I will discuss my examples in the following. This is, first of all, this is just for our fundamental understanding what's going on in these materials, but there has also been some suggestions that one can use this for functionalities, for applications maybe. There is this concept of the Mott transistor where you drive this phase transition by some external stimuli, and you go from an insulator, that's the off state of the transistor, to a correlated metal, which is then the on state. And the important point is that if you have a certain amount of valence electrons in your systems, all of these electrons will collectively take part in this transition. Whereas in a conventional field effect transistor, it's only the doped electrons, not the ones that are already present in the system and are responsible for the insulating behavior. It's only these extra electrons that drive this transition. Here, it's all electrons, all d electrons taking part. There have been some suggestions how you can achieve this in principle on the theory side. The question is, how can we do this experimentally? And the idea is you take a simple Mott insulating material or strongly correlated 3D oxide, for example. Here's a number of systems. In this case, these are titanates and vanidates, which all share the situation that they have a D1 ground state filling. Some of them are insulating, some of them are metallic. And then you try to drive these systems through this phase boundary here, or put them very close to the boundary and do the rest of the transition by some external stimuli, by doping it by field effect or by straining it or whatever you can think of. But for that, you need, first of all, to grow these materials as thin films, because at the end, you want to make a device out of it. So you cannot do it just with a simple single crystal. You want to do it with thin film, epitaxial thin film deposition methods. And that's some challenge, as I will show you here, for example, for the case of lanthanum titanate, which is one of the prototypical mod insulating systems in this business. Here's some information or some data on the growth. LaTIO has been studied a lot as a bulk crystalline material, but here we wanted to grow it by pulse laser deposition, and we were certainly not the first group to do this. There are a number of other groups that have tried this before and have done this. You can grow it on a suitable substrate. Here we have used strontium titanate and also dysprosium scandanate. And you see very nice read oscillations here. You can monitor the read spots, look at the crystallinity. You can look at the surface ordering here, which tells you a little bit, as we can see later, on the oxygen ordering on the surface. And you can do this with very nice layer by layer growth, so that you can really count the number of layers you grow. There is one problem with LaTIO, and that is that this is very sensitive to overoxidation. It likes to absorb extra oxygen into its structure, so that you never, or that it's very hard to get a clear lanthanum titanium O3 stoichiometry. Very often you have some 3 plus X here, and that you can already see in the X-ray diffraction pattern here. These are 3 XRD patterns of LaTIO films that we have grown in various oxygen background pressures in the PLD. This is oxygen poor, or you could call it already vacuum. This is 10 to minus 6, 10 to minus 5. And you see, as we increase the oxygen pressure during growth, this is the peak. It's a broad peak because it's a very thin film. You see, however, that the peak here is moving towards smaller angles, which means that the lattice constant is increasing as we have put more and more, have more and more oxygen supply here in our growth. And this is an indicator that extra oxygen is incorporated into the lattice. You can see this also in the HAXPES. You would expect for stoichiometric LaTIO that you have trivalent titanium, which means that you have a D1 situation, titanium 3+. If you look at the spectrum here, grown at 10 to the minus 5 millibar, you find here in blue our 2p spectrum, and it has almost exclusively a tetravalent titanium in it. So that's titanium 4+, a D0 situation. That's certainly far away from 3+ as it can get. There's just a tiny little satellite weight here in the 3+ peak. If we reduce the amount of oxygen during growth, going towards the red spectrum, you can see that we increase this trivalent component, so that we increase the occupation of the D shell, but there is still the dominant 4+ weight here. So we're still away, quite a large way away from 3+, and that's due to this extra oxygen that we have here in the lattice. The question is, where is this extra excess oxygen located? And it helps to remind oneself that there is a related compound, lanthanum 2 titanium 207, which is related to our original 113 perovskite phase by the introduction here of extra oxygen, double oxygen layers every 5 unit cells, every 4 unit cells here as you go in here. That's the 2207 phase. Now, one could think, of course, that if you have extra oxygen here in the growth, that you start forming this 227 phase coherently at some portions of the sample, but we never saw any indication for that in our X-ray diffraction data. So what we think what happens is that you have excess oxygen somewhere here incorporated in our 113 lattice in a similar fashion as it is done in the 2207, but these are statistically distributed throughout our lattice, so they don't contribute to coherent X-ray diffraction. So that's why we do not see them as a clear Bragg peak, but we do see them here in a slight expansion of the lattice. The question is, where does this excess oxygen come from? Here, it's very likely, or very obvious, that this might be related to strontium titanate itself. We have seen before that strontium titanate likes to get rid of this oxygen. LaTIO is a material that likes to suck extra oxygen. So you combine two materials, which then collaborate in the way that oxygen will be transferred from STO to LaTIO. So maybe STO is not the best possible substrate for growing LaTIO on top of it. So that's the picture that we have, that some of this oxygen is diffusing out here during growth into this LaTIO film. This is again a 2p spectrum, titanium 2p spectrum, where you see this distribution of 4+ and 3+ weight. We could try to suppress this diffusion by putting in a diffusion barrier. So we tried to put LAO in between. And as you can see, this does help a lot. So we reduce the amount of 4+ signal and 3+ goes up, but there is still a lot of titanium 4+. So it does not completely cure our problem. It goes the right way, but not all the way that we need. So maybe we just use a different substrate that has a more or less similar lattice constant. Here we use dysprosium scandinate. It's a material that does by far not produce oxygen vacancies or like to form oxygen vacancy as easily as STO. And if we use DISCO, you can see it does indeed go even further. Now finally our 3+ signal, the 3D1 configuration, dominates our spectrum, but there's still a sizable amount of 4+. The question is, where do these D1 electrons sit, or where do these extra electrons sit in our LaTIO film? Because maybe they do not come from the DISCO at all. Maybe they come from the vacuum, because as I told you yesterday, the vacuum is never perfect. There's always a certain residual amount of oxygen in our vacuum chamber. And you can probe this by doing, again, a depth profiling measurement. So we change the detection angle here in our experiment. As we go from red to blue, we go from bulk to surface sensitive conditions. And you can see, indeed, the 4+ signal increases strongly as we go to surface sensitive conditions, and the 3+ gets depressed, which means that the extra oxygen that we still have in our sample is sitting most likely at the surface or confined to the first or second layer of our LaTIO film. That's a result you can directly take from this angle dependence. And the picture that we have here, and that's very consistent with a lot of studies that we have done recently on other perovskite systems as well, is the following. From the growth that we have done, we start with a titanium oxygen terminated substrate layer, or in our case, it's the dysprosium scandinate with a scandium oxygen terminated layer. Then you start growing the titanium, the LaTIO on top. And then you, in principle, you end up with this titanium oxygen layer of the LaTIO. But that means that the titanium atoms on the surface don't see a full octahedral coordination of oxygen atoms, which is energetically unfavorable. And so what the system tries to do is, whenever it can capture an oxygen atom from the residual gas, it will bind it here to the surface in order to complete this octahedron. Of course, this will then be an oxygen 2- ion, and this will lead to a p-doping of the residual system. So it will reduce the valency from 3+ to 4+ at this first or maybe even second layer by attracting electrons from the first and second layer of titanium atoms. And that's what we see in our spectroscopy. And in order to prevent this to happen, what we need now is to cap our surface here with some other oxide that takes care of this completion of the octahedral coordination of the titanium without p-doping the system, and that we have tried to do by putting an LAO cap layer on top. By that, if you count charges here, you would end up with the titanium staying in this trivalent condition. And here is our situation. If we start from the LTO on the disco, which is the green spectrum with a bare surface, still a lot of 4+, but hardly any, and a lot, some 3+, but still a lot of 4+. And then we put this LAO cap on the surface, and you can see that we have a strong increase of 3+ and hardly any 4+ signal left. This is the spectra, and we have not only now reached a situation where we really have dominating 3+ D1 configurations, it's also capable of protecting now our film from further oxidizing when you expose it to ambient atmosphere. For example, this is what we call in situ and ex situ. In situ means we have grown our crystal in our ultra-high vacuum chamber and in the PLD chamber. We have transferred it under ultra-high vacuum to our photoemission chamber and measured the 2p spectrum. And ex situ means we have taken the sample out of the vacuum system into air, expose it to ambient atmosphere, and put it back in the vacuum to measure its photoemission spectrum, and you see there is no difference. So there's no extra oxidation of the LTO. The LAO really works as a capping that protects also from oxidation in the air. That is important because if you eventually want to build a device, you have to process your films in an atmosphere which is certainly not UHV, which will contain oxygen, and then you have to make sure that you don't get a further oxidation of your LTO film. So this is the valence band spectrum that you can measure. Again, we go into a resonant photoemission condition where we can enhance the intensity of the 3D weight. And you see here the oxygen 2p valence band, and this is the 3D spectrum. It's basically a single peak here, and there is no Fermi edge here. So this is really an insulator. We can detect or roughly measure the gap by extrapolating the onset. The finite tail here is due to the instrumental resolution in this experiment, and you get something of the order of a few tens millivolt of a gap, which matches very nicely what is known about bulk LTO. So we are in a situation where we are now in this region where our LTO is a Mott insulator. We have succeeded in growing a Mott insulating thin film of LTO, which is basically fully stoichiometric. There is no excess oxygen. Now the original idea was to move our sample close to this boundary here so that eventually we can switch it back and forth across this boundary. So now we need to start doping again. And we can do this, or we have seen already that oxygen depletion means that we have some kind of p-doping. And we can do this now by going back to the situation where we have a little amount of excess oxygen in our sample. So we go from this situation here towards this boundary. We actually cross this boundary now and go into a metallic regime. And this is shown here. And if you do this, you find in the valence band that we have now a second peak popping up here. We have our original lower Hubbard band here, but now we have an additional quasi-particle peak. This is exactly what you would expect from the Hubbard model or from DMFT calculations of the Hubbard model. You have a lower Hubbard band, you have a quasi-particle peak, and you would have an empty upper Hubbard band, which of course we do not see in photoemission. You can actually also probe now the Fermi surface of this metallic quasi-particle in this strongly p-doped LTO. This is shown here. Here you see what you would expect from band calculations, and this is basically what we see here. We see these tubes. Basically, what you expect to see are these tube-like structures in LTO that are oriented along the X, Y, and Z direction, and this is basically what we see here as well. And then you can, once you have these kept samples, you can also look at the transport behavior, and this is shown here. as you change the growth pressure, large oxygen pressure means that we strongly dope the system with excess oxygen, so this leads to p-doping as we go from blue to red. We start out with a situation where we have achieved this insulator. We put a little bit of more oxygen in, still an insulator, even though the resistivity has decreased a little bit. And as you go across a certain threshold, you find that you cross this boundary towards a metallic situation and you find this metallic conductivity. So spectroscopy and transport is fully agreeing here. And that's a good starting point for looking at playing around with this now in device type geometries. But let me go to another example here, strontium vanadate. And here we do a similar thing, except that now the mod transition will be controlled by the thickness of the film. Strontium vanadate is a material that is in the bulk not in a mod insulator, because the U is not big enough for that. The correlation is there, but it's not strong enough to render the system mod insulating. And so we are in the phase diagram at this position here. But it's a 3D1 configuration. It's vanadium 4+, as we have it, it's 3D1 as in LTO, but it's a metal, but strong correlations are reflected in the fact that this is a strongly correlated metal. So the mass renormalization, the effective mass that you find with respect to the band mass that you would get from a bare DFT calculation is a factor of 2. That's a strongly correlated system. And if you look at the valence band spectrum, you find indeed a metallic situation. The red spectrum here is from the SVO grown on STO. You see here the quasi-particle that you have in this system, even in a D1 configuration. And here you have the lower Hubbard band, while for comparison, here's the LTO spectrum. You have this lower Hubbard band, which has no evidence here of any quasi-particle weight because it's a mod insulator. This is the transport of such a film. It's clearly metallic. You can actually fit it very nicely with a t-squared behavior. This is the resistivity versus t-squared. So one could be inclined to identify this as Fermi liquid behavior, but I'm not so sure if this is really all the way Fermi liquid type t-squared to room temperature. Typically, the Fermi liquid regime is more at the very low temperatures, and this may be due to the phenomenological t-squared behavior, may be due to other effects as well. But it's clearly metallic. You can also look at the Fermi surface. Again, that's a Fermi surface picture, or this is similar to LTO. There are some fine details that are different, but you can trace this out nicely. But what I want to drive at in the following is that we can drive the system into an insulating state from the metal by going to thinner and thinner layers. So this is our schematic picture. We start out with a thick layer, say 75 unit cells, and then we grow it thinner and thinner. And as we go towards 6, 5, 4 unit cells, you can see that the quasi-particle weight is going down here. We still have a little bit of a Fermi edge, but as we go to 3 or 2 layers, you see that spectral weight is moving away from the Fermi level, and we run into an insulating situation, meaning that ultra-thin strontium vanadate is no longer a metal. We are not the first to see this. There was a paper a few years back by Hiroshi Kumigashira's group at the Photon Factory that have seen the same effect to happen. And the picture is, as we go from the bulk phase, from thick films to thinner films, we kind of freeze out the motion of the electrons along the third dimension, meaning that the kinetic energy becomes smaller and that the relative weight of the correlation effects becomes stronger. And then you move in this phase diagram into this mod insulating regime until you cross at between 4 and 3 unit cells, this boundary conditions, and then you get a mod insulating behavior. Now this is a little bit tricky to look at because it turns out that there are some extrinsic effects that you have to be able to control, and one of them is again some kind of surface oxidation. If you start out with a thick film here. You measure it immediately after growth. You have here some 4+ signal, but there is also some 5+ signal as well, which does not completely go away. And if you expose it to air, to ambient atmosphere, and put it back into the photoemission chamber, you see that there is only a pentavalent vanadium left. So we are in a D0 situation, but we would like to have D1. So how can that be? Again, this is a surface effect, as can be seen here by the angle dependence. As you go to surface sensitive detection, you find that the 5+ signal is increasing. So the problem really happens at the surface. And again, it's this completion of the open octahedron by extra oxygen getting absorbed at the surface. But again, extra oxygen ions mean that you reduce your you oxidize your metal ion, and so you drive it from 4+ to 5+. And this is what we see here. Actually, you can see this also in the lead, because if you are in this situation, you see extra spots in the lead, which is due to oxygen vacancies on the surface. Oxygen atoms on the surface, which form a regular pattern and lead to a square root 2 by square root 2 superstructure. And you can model this in density functional theory calculations. This has been done by my colleague Giorgio Sangiovanni and his student Marius Fuchs, where they have looked at the situation. For us, we are interested here in the top line. If you have this extra oxygen sitting on the surface, it will deplete the deoccupation here of the vanadium at the surface, while the vanadium atoms a little bit deeper under the surface, this is calculated for a 3-unit cell system, are closer to a D1 situation. So what we see in the experiment is confirmed by the band calculations. And in order to get rid of this effect, again, you can grow a cap, a protecting cap on the surface. This is shown here. Here we use SDO on the surface. It can be nicely grown on top here. You see here the reed oscillations. And this is now vanadium 2p spectra. On the top, I show you the spectra of an uncapped sample measured at different probing depths. The black one is the surface sensitive situation where we have a strong pentavalent vanadium signal. As we do probe a little deeper, we see more and more of the vanadium 4+ multiplet structure, but still a little bit of residual 5+ weight. If we use a capped sample, we see a very strong suppression of our pentavalent signal and are left basically here with the intrinsic vanadium 4+ multiplet. You can also show that this protects against ambient atmosphere. If we have a uncapped surface, again, the red spectrum is as grown in situ. The brown one is after exposure to ambient atmosphere. Everything is 5+. I see Jochen moving. I still have a few minutes, do I?
Yes.
Okay, I'm almost done. If you have a 4-unit cell cap, you can already see that we suppress the pentavalent signal here, the surface effect. If we have twice as thick SDO cap, you see there is no difference whatsoever between the in situ grown material and the exposed material. So that's really protected against over-oxidation from ambient atmosphere. And then if you look at the capped samples and look at the transition, you find this is transport data on these samples. This is the corresponding spectroscopic data, and they agree that the transition now between the metallic regime and the Mott insulating regime is now more at somewhere around 6 unit cells, not the 4 unit cells that you have for uncapped surfaces. This is the data that we have done for the uncapped surfaces. And this tells you that maybe the naive picture that we had in the beginning, where I have argued that making the sample thinner and thinner freezes out this kinetic energy. We go from a 3D to a 2D limit, maybe not the correct description, because at 6 unit cells, we are not really in the 2-dimensional limit. So what one can speculate at this point, and there are a number of theorists looking at this at the moment, that as we go to thinner films, what happens is that we have a certain structural relaxation in these films, which are the tiny bit that is enough to drive the transition from metal to insulator. But that's not really fully understood yet. Okay, so what this would describe now the situation in the SVO case. If we have uncapped samples, we would go here both in the direction of changed filling, because we have the surface oxidation, as well as a change in the correlation strength. Whereas in the capped films, we would argue we have frozen out this p-doping effect or a doping effect, and we go all the way vertical from D1 metal to D1 insulator. And I would skip this last part here on the iridates. This was just for reserve anyway, and summarize here for these correlated systems. Iridate would have been a similar system where spin orbit coupling plays an important role as well. So we've been studying how you can drive a mod transition in these D1 systems, and how you can control both the oxygen stoichiometry and also the thickness. And the next step would be to look at real device structures. And the first thing that we have tried recently in March actually was to grow such a system where we have a capped SVO film with a dielectric below it and some metallic gate in order to gate it here. And we wanted to study it in situ, in operando, in the synchrotron. But as soon as we had finished the sample here, they had closed down all synchrotrons due to the corona situation. And so that's where we are stuck at the moment. Okay, and with this, I want to conclude. So we have been going from studying these systems from very fundamental understanding with the goal to eventually also control and design functionalities here. And our approach was basically based on photoelectron spectroscopy, which gives you all these very nice access to all these microscopic electronic informations. Just as a final outlook remark, there is a lot of instrumentation development and method instrumentation going on at the moment, which we are involved in. This concerns spin detection with multi-channel methods, which is important, of course, for systems where magnetism plays a role. In operando spectroscopy, I just mentioned that we want to look at samples that are driven by a gate field and look at the spectroscopic information that we can get under this gated situation, up to all the way to develop a new analyzer generation, which goes by the name of momentum microscopy, which would give us a much enhanced intensity detection compared to the conventional types of photoelectron analyzers that we are using at the moment, but I didn't have time to talk about this. If I could get you interested into this topic, or if you know someone who's interested, we have a number of PhD and postdoc positions that are available, and if you're interested, just contact me. And with that, I want to conclude and just mention there's a lot of interesting literature that you can look up if you want to know more about this topic. Thank you very much.
Thank you, Ralph. This is very impressive to see which detailed insights photoelectron spectroscopy can give into oxides. That's beautiful. We have actually a row of questions coming in.
Okay, good.
I'd like to handle them just in the sequence as they arose. The first two ones are actually related. So I'd like to ask Pushpendra Gupta and Ruby Km to open their microphones and to ask their questions, starting with Pushpendra first.
Hello, sir.
Yeah, if you speak a little bit louder, it would be better.
Hello, sir. Now it is audible?
Yes, I can hear you.
So thank you, sir, for the nice lecture. And my question is, sir, if you prepare some STO film in PLD system with, and you have some deficiency of oxygen in the film. Then you are doing dosing of oxygen. Then, sir, the pressure of oxygen in the chamber what will be the effect of the pressure of the oxygen in the chamber? And sir, what are the temperature role in the, means high temperature is needed or what, like?
You mean these dosing experiments?
Yes, sir.
Yes. First of all, the background pressure is extremely small. That's the reason why we use this capillary method. It's very close to the sample surface. It's as close as a millimeter. And when you dose it and you measure the background pressure in the photoemission chamber, it goes up from 10 to the minus 10 to 1 times 10 to the minus 9 at most. So it's detectable, but hardly so. But that's the background pressure. The pressure immediately before the surface may be quite much higher, but of course we don't have a detector in front of the sample. What we see, however, is that there is a strong effect. We do see this reoxidation directly in the spectrum. What are the temperatures? The surprising thing is that we do these experiments with cooled samples. We do this at typically 50 Kelvin. If you look at bare SDO, the oxygen atoms do not have to diffuse very far, so that's not a problem because then everything happens at the very surface. For the LAO SDO system, if you want to fill the oxygen vacancies in the strontium titanate substrate, of course the oxygen that we offer to the system have to diffuse through the LAO. It's only 4 unit cells or 6 unit cells typically, but nonetheless, they have to diffuse through this, and you would think at 50 Kelvin everything is frozen out, but from what we see, from what we observe, that doesn't seem to be the case. So the oxygen does seem to end up in the SDO interface.
Sir, actually, this during dosing experiment, you are supplying oxygen through the tube. So in case if temperature is low, then the STO substrate is STO film is getting reaction with oxygen, or you need temperature, a high temperature for that.
No high temperature. Everything is at low temperature.
Okay, sir. Thank you, sir.
You're welcome.
So Rubicon had a very similar related question. Do you want to pose it again, or do you think it has been handled?
I think my question is already answered with previous question. Thank you all so much.
Good. Okay. So let's go on to the third question here in the row, which is posed, if I pronounce the name correctly, by Xishao Wang. Please go ahead.
Good morning, Professor. Thank you for the nice talk. Hello?
You're welcome. Yeah, good morning.
Hi. So my question is, when you're discussing the Lassmann hallucinate and strong titanium oxide interface, you mentioned the oxygen deficiency. But do you also consider some reports also mention that there could be Lassmann diffusion, which is can penetrate from the Lassmann aluminum oxide into the strong titanium oxide, and that may also cause this unbalance of the stoichiometric strong ions and the titanium ions, and it may also create the 3 plus titanium valence. What do you think about this? This kind of?
Yeah, yes, we thought about this. It's much more difficult to study. You're talking about off stoichiometries of the cations, and this also involves the question of the existence of cation anti-site effects. Well, in this, the nice thing about the oxygen or the effect of the oxygen stoichiometry is that we can change or tune in situ the oxygen stoichiometry very easily. It's not so easily done for the cations, obviously. You would then have to measure the direct stoichiometry of say lanthanum versus aluminum, which is much harder experiment, because then you need to calibrate your signal to a nominally stoichiometric compound. There has been very recently been some extent and some experiments which will be published soon, where people are using X-ray standing wave methods. What you can do is you can use your exciting X-ray radiation and let it scatter off from the crystalline lattice of your substrate, and then by that you can create standing waves of your X-rays, and then you can tune the intensity maxima of this standing wave field through your film, and by that then probe the position of the lanthanum and the aluminum, for example, ions. And there is one report where they claim that they see some indication of the formation of such anti-side defects that were proposed or suggested by the theorists around Alex Lunger's group. But for the experiments that we are doing, we haven't done this because it's so difficult to control. We do not do these X-ray standing wave experiments. So clearly, the oxygen does play a role, as you have seen. I mean, changing the oxygen stoichiometry has some effects, but I'm not claiming that this is the only effect. I have shown this residual intensity of quasi-particle weight in the LaO, and that must have a reason, and it's not due to oxygen vacancies. That's for sure.
Okay, thank you.
Okay, you have a follow-up question. If you want to pose it again, if you want to pose it too, please go ahead.
Okay, so I will just ask for the other my questions. So I have read the Philippus PhD thesis, really nice work. So you mentioned that the STO is the oxygen conduction substrate, which is diffuse oxygen into the lanthanum titanium oxide film. That's why you choose the DSO. But do you also expect other substrates cannot be oxygen conductive substrates?
Yes, you can. Of course, you can also use other substrates. I mean, we have picked DSO because of its oxygen stability for once, and then also for its lattice constant. We have been trying also a number of other substrates, but DSO was the one that was most easily controlled and gave the clearest results. And but you can play around with it, and in fact, we have a number of studies going on where we use the strain as an additional tuning parameter as you use substrates with different lattice constants and see what effect they have on the lattice. That's particularly interesting for the LTO.
Yes, thank you. Last thing is, I noticed that when Philip deposited the films, he used extremely low fluence of the plume to inject the ions from the target. Do you have any mechanism to explain why when you have the 227 targets and then you require such a low fluence to achieve 113 stoichiometric film?
Say again, I'm not quite sure if I caught the essence of the question. The question is why we do not see a 227 signal, or?
No, I mean why in the experiments you use such low fluence, only like 0.9 or.
Well, we simply we have every time we start with a new system, we're exploring the phase space of the growth parameters, as I'm sure you're also doing. So we change substrate temperature, we change fluence, and it just happened so that this seemed to produce the best results.
Okay, do you have any mechanism assumption why?
No, not really. No, not at this point. Okay. Sorry.
Thank you.
Good. So I'm not forgetting Jonathan Spring, but I'd like to go ahead with the question of Leo Kambu, because that also fits a little bit into this type of questions that have been asked right now. So if you like to ask your question, please unmute your microphone and go ahead.
Yes, do you hear me?
Yes, I hear you.
You presented us a model on LaTIO where we can have interstitial oxygen that might explain the titanium 3+4+ ratio. I'm wondering how to be sure that this model is actually the one that we have. If I want to confirm this model, what kind of experiment can I do to?
You're referring to LaTIO, right?
Yeah, LaTIO.
So you're asking. Yeah.
We have a kind of similar system on DTO.
Yes.
With titanium 3+, and we want to come up with a model, and we actually looked at this publication, and we were wondering how can we confirm that this model is actually the one that we have.
I'm not quite sure what you refer to as model. I mean, I have this picture that we ought to have a trivalent titanium atom, and very often we do not see that. Very often we see only 4+. And then by systematically changing the different substrates, by putting in this diffusion barrier, the LAO between the SDO and the LTO, by putting up a capping layer, by looking at the depth profile, by changing the photoemission escape angle, we get this conclusive picture that some of the oxygen this excess oxygen comes from the substrate, and that has to be avoided by choosing a suitable substrate. And some of the oxygen comes from the residual gas in your system and oxidizes the surface. And that's the picture. I'm not quite sure if that's a model, but if you want to understand where your off stoichiometry comes from, you have to change the conditions at the interface. That's you do by changing the substrates, and you have to change the conditions at the surface by either capping the surface or looking at the surface profile. Not sure if that answers your question.
No, okay, I understand. Thanks.
Okay. Now we come to the question of Jonathan Spring. Please go ahead.
Yes, thank you. Could you please elaborate a bit on the difference between HAXPES and XAS? Because as far as I understand, they can extract very similar information. So for a specific experiment, how would you choose between the two techniques?
XAS, you mean X-ray absorption spectroscopy?
Yes, exactly.
Yeah. Well, depends on your perspective. I would not say that they are very similar. They are quite different, actually. Well, in XPS,
so for example, you showed a lot of data where you compared different valence states, for example, for a titanium atom, and that's something you can also quite easily extract with X-ray absorption, right?
Yes, that's true. That you can do for example, for the titanium valency, you can either look at the titanium 2p core level in XPS, which gives you direct information about the valency. X-ray absorption, the same is true because the absorption spectrum for a trivalent and a tetravalent titanium atom is very different. You have to be careful though, because we found that the reference spectrum that are often quoted in the literature for the trivalent spectrum very often include a very strong titanium 4+ contamination in them, because people haven't often realized that you always have a very strong 4+ contribution.
Yeah. Okay.
That's one thing that works in this case quite well. Generally, it's always a little dangerous to use the X-ray absorption data, because that's really you have two states that are playing a role here. It's the 2p from which you excite, and it's the 3D into which you excite. And you may have. If you use it as a fingerprint, if you have nice reference spectra and you use it as a fingerprint, that's fine. If you try to interpret it, you have to be very careful. Very often people interpret X-ray absorption in terms of unoccupied density of states.
Yes, exactly.
Which is not correct, especially not in 3D transition metals, because you have very strong excitonic effects. So you cannot neglect the many body effects that you have in there. That's a problem that is less severe in HAXPES because you create a hole in your state. You may have multiplets, of course, that you have to be aware of. 3D electrons can interact with the core hole that you have. Nonetheless, it's easier to interpret, whereas an X-ray absorption spectroscopy, that's often very difficult. If you I just try to remind you of X-ray absorption work on high TC cuprates. People have always looked at the oxygen K edge because that's not so strongly affected by these excitonic effects as opposed to the copper L edge, because that's a mess if you try to understand it. You can understand it, but certainly not in terms of a single electron picture.
Okay, thank you.
Good. So I don't see any further questions here on the chat. So this is your final chance. If you'd like to ask a question, please go ahead. Nothing happens. So let's thank Ralph Claessen again for this very clear and I think also beautiful introduction into photoelectron spectroscopy and its power. Thank you, Ralph.
You're welcome.
And to all of you, have a great day and do something wonderful with it. Bye-bye.
Bye-bye.